Welcome to pre-calculus video for skill number 21. I can describe graphical behavior including end behavior with limit notation, finding local extrema, and concavity. There's no trivia question for today's video, but I wanted to point out how far magnetic south is from geographic south. Magnetic north and geographic north are also pretty far separated, but this deviates over a distance of about 20 miles. I guess that the question you could ask yourself is, how does one find the geographic North Pole if they can't use a compass? Alright, we'll start our notes on page 21A. And rather than getting into the technical definition of all of these, I just kind of wanted to show you examples of what each thing is. So the first one we have is end behavior. And end behavior is what exactly is the graph doing at the end. So for this function, f, as we go all the way out to infinity, our graph just keeps climbing and climbing and climbing. So you could say the limit as x goes to infinity of our function is infinity. If we wanted to know what was going on as we moved leftward, it looks like our curve just keeps going down and to the left. So you could say the limit as x goes to negative infinity of our function is negative infinity. Let's take a look at an example that is not infinite. Here what we have is a exponential curve, and this exponential curve appears to be dropping down and getting closer and closer to the value of 1. So as x approaches infinity, the curve approaches the value of 1. So we say the limit as x goes to infinity of g of x is 1. In the opposite direction, our curve goes up and just keeps going up. So the limit as x goes to negative infinity of g of x is positive infinity. Alright, our third example, we have a curve that goes down in both directions, so it's down and out for all eternity. So the limit as x goes to infinity is negative infinity, and the limit as x goes to negative infinity is negative infinity. This function is always down and out. Sad function. The next term that we should know is Localis Extrema, and the local extrema can actually be broken down into local maximum and local minimum. And a local max occurs at x equals a if f of a is greater than f of x near that point. So in our first example, we have a local maximum right here, and as you can see, that's kind of a high point in the curve right there. So we say we have a local max of 3, 1, 2, 3, so a local max of 3 at the value x equals 2. If we look at our second graph, we see that we actually have two maximums. We have a local max of 3, and we have a local max of 6. Our first maximum occurs at x equals negative 2, and our second local max occurs at x equals 4. So it's important to note the order of these numbers. So the maximum is the y value and the location is the x value. A local minimum occurs at x of a if f of a is less than the function near x equals a. So in this case it looks like we have a spot that kind of comes to a local minimum there, and then we also have what looks like a local minimum right there. So we have a local minimum of 2 at x equals 1. X equals 1. We also have a local minimum of -2 at x equals 1, 2, 3, 4. Did I really do that? 1, 2, 3, 4. Oh, hey, look, typo. X equals 4. So we're our local minimum there. Alright, the next piece is increasing and decreasing, and this is far more evident. We can see that as we move from left to right, the function is increasing from -infinity to -3, and then it's also increasing from -1 to infinity. So that's our intervals of increasing function, and then our function is decreasing from -3 to 1. So that's our interval of decreasing function. Our second function, if we look closely, we see that it is always decreasing. Even though it's getting really flat, the further to the right we go, it's still decreasing. It's getting closer and closer to that asymptote. So we say the function is decreasing on all real numbers, or from -infinity to infinity, and that it's increasing nowhere. As we move up to, or down to concavity, so concave down means that the graph has some sort of like downward shape, whereas concave up means the graph has some sort of like upward bowl shape. So in this graph, our concave down region happens from -infinity to, it appears to be 0. At 0 we have the point of inflection. So the point of inflection occurs when we switch from concave down to concave up, or vice versa. And then our concave up portion is from 0 to infinity. In our second graph, we've done a switch twice. So we start with our concave up portion, and we wind up getting a point of inflection at -1. And then we flip to concave down for a little while. So our curve is kind of opening down, and we get a second inflection point at x equals 3. And then the curve switches back to being concave up. Alright, so that concludes the video for 21B. You should be able to describe graphical behavior using limit notation. So that's saying the limit as x goes to infinity of our function, maybe that equals 7. You should be able to describe local extrema, which would be finding the maximum or the minimum. You should be able to describe concavity, so you have concave up or concave down. And then, though it's not listed here, we should also be able to identify intervals where it's increasing or decreasing. Thanks for watching.